Good morning, everybody, and let me introduce the topic of my presentation, which is there on the slide. And I think this is a good example of the structural integrity analysis of the 21st century when we are moving, we still continue working as was presented now in the aerospace and other applications, but biomedical applications are becoming more and more important because of the transition to the personalized medicine. And I would like to show you here one of the possibilities in this way, and so just the challenges which are related to it. So, but before this, I would like to invite you to the conference, which is dedicated to the analysis of the biological and biomedical materials, which will be organized in a nice place here. So just it's slightly different from Rome. So just, but there is still time to submit your abstract. And now, without any further ado, let me go just to the presentation. And here is the type of the engineering device, which hasn't changed much in principle from the 18th century. The only difference probably is the change in the materials. And to get the idea about the modern challenges, let us consider that this socket, which is presented here, which is being made of just either metals or nowadays polymer-based composites. It is 5 orders of magnitudes stiffer than the soft tissue. And inside the soft tissue, there is a bone, which is also the same orders of magnitude stiffer. So we have a very short transition between these two materials, and mismatch is a very significant one. So this clearly raises quite very interesting problems on the modeling part, but today I'm focusing on the structural integrity, and I would like to demonstrate the behavior of this type of the materials. And for you to understand generally, even up to now, with all our technology, the production of the sockets is more type of the art than the science. It's a very long artisan procedure where each limb is being measured several times, and then the socket is being manually adjusted, not in the way different, so just how the sculptures are being made, but the sculpture is an internal one, clearly, and then so just people are using it. And another point to remember, generally one socket is needed on average, 1.5 to 2 years. And if you are, so just if the case is of the children pediatric sockets, they need them every 3 months. So this is a very serious problem. And clearly now we all know about the potential answer to it. It is 3D printing, because you can produce this type of the sockets if you know the geometry straightforwardly indeed. And so these are the already mentioned challenges here. And this is what we are going to demonstrate you. So just let me show you a very quick video. So I will even accelerate it. Oh, sorry. It doesn't run. Okay. Here it is. So it's generally to demonstrate to the entire process, it would take 48 hours on a modern printer to produce one socket. And this is just for the 15-year-old male. And so still it is significantly better than to do this in any other way. The interesting point here is that though we have the standard, which is demonstrated here, there is not much information about this. And as you can imagine, this is not a material, this is a product. So that's why the type of the loading and conditions is very straightforward one. They are prescribed and they're related to the different stages of the gate. So this caused us to design a special test rig, because clearly when we are moving, depending on the gate, there is a change in the direction of the load, which should be reproduced in the testing device. And you can see here the types of the different conditions. The first one is the strike of the foot, and the second one is the separation of the heel from this. And this is another way, so just this is part of the model which presents here the major materials which are being used in this. Currently, there is no suggestion what type of the material should be used as a model for the limb. People are using gypsum because it's easier to produce this, but clearly the properties of the muscles are totally different from gypsum. That's why we were using, for instance, silicone. And these are the types of the results that are produced in this type of the loading. You can see here the complex shape of the socket. And as a result, you can see that after this type of the loading, there is a formation of the crack, which is going in the circumferential direction here. It is in the condition 1, which is being tested. And in the condition 2, which is shown here, so just for the black leg presented here, we have not achieved the full fracture of this socket, though we've seen some discoloration as a sign of the arrangement of the appearance of the cracks. But the important point is that all this was obtained for the significantly higher levels of the loads that are supposed to be achieved in this. Also, so just for you to understand how it is considered, the standard foresees a 5-fold weight, which is supposed to be carried by a single socket. So just practically, it's a factor of 10, because usually, as you can assume, though, in standing, it's only your weight is divided by 2. But when you are going, in this case, it is it's supposed to be 5 times higher. These are a very short result, because I'm aware that I must finish very quickly. Short result of the simulations, which demonstrates to us that this complex type of the model, I'm shown here the socket, but we have modeled the entire system, which also incorporates all the elements of the loading device and the type how it is being applied. So it reproduces and explains the amount of the displacements and the resulting forces. In the condition 1, you can see that the displacements, maximum displacements around 5 millimeters, which is sufficient to cause the cracks at the highest level of the load. While in the condition 2, sorry for a typo, which is at the bottom, it is only roughly 1/2 of this amount. And now these are the most important results considering the experimental studies. And here you can see generally that we can have here the results of the simulations, which are in the blue line, which are much better reproduced in the condition 2 than in condition 1. The important part is the horizontal dashed line, which demonstrates to you the load-bearing capacity of the socket, which is supposed to be performed for any device of this type. And as I've already mentioned, that all the 3D printed sockets, they have successfully met the condition 1 criteria, exceeding this level by some margin. For the condition 2, we demonstrate that effectively, even at significantly higher level of the load, the socket still continued to bear the load with any significant failure occurrence in the socket. So that's why it's clear for everybody sign that we can still continue reducing the parameters like the thickness of the socket. Also, this type of the socket in the result of the printed was already 15% lighter than the one produced with the traditional ways. And so just very quickly here, so just I wouldn't go through the conclusions. I prefer to have some questions here, and because just all these major points were made in my presentation. Thank you very much for your attention.